Okay. Oh, wait, my voice is up. Okay, I think that's the time to start. Welcome, everybody. I spent a little time rechanging the title. Just the content is the same, but I think this explains a little more what I'll be talking about. Unity, so first of all, my name is Issam. I'm work for Intel. And we've been following the job system and ECS for a long time. We were talking with Unity, trying to figure out how it works. And we're really interested in it because we believe it has the potential to allow you to use your hardware to the real capacity of what the hardware can do. And I wanted to take some time today to kind of go around from the hardware perspective side, kind of explain, well, why should you care? Why is it important? How can you end up using it? And just to say, we have a group at Intel that's here to help game developers be more performant. We have a booth at the kiosk if you want to go and get more information. And you can also email me if you have any questions specifically, and I can put you in touch with people. So we're always hoping to help people get the more performance. In terms of me personally, I've joined Intel 2 years ago. Before that, I've been working for, at this point, maybe 14 years in the game industry. I started on Madagascar, GBA. I don't know if anybody played that game, but it was my first game, and I'm proud of it. Then Tony Hawk DS, which was the first Wi-Fi networked game on the DS. If you go to Wikipedia, it will say the first third-party game, but that's just because Nintendo decided to release their game first. Until, in practicality, we made it first, which is okay, pointing that out. And then I kind of kept working all the way to Scalander, kind of become a performance engineer, worked on porting console games from the PS4 all the way to the iPad, and working on performance a lot. And then I moved to Intel to help with the performance specifically on the PC. So I guess I have a clicker. I don't need to go there, but sorry. So my plan for today is kind of going to be I like when I talk about performance and explaining API and kind of why things happen, to go back to a high-level overview. Generally, we focus on the low level. We start looking at technicality, and we forget that there is an assumption at the start, a reason for things at the start where things were made. And when we break those assumptions, even if we focus on the technicality, we won't really gain performance. We have broken the initial assumption we made about why stuff on the hardware works the way they work. So I want to kind of go start thinking about, as a software engineer, I've worked in game a lot, I've worked in code, I've kind of stuff. The way I was thinking about performance before was wrong. And I'm kind of going to talk in the way I was thinking, and in the assumption that it's kind of also the way I believe people are kind of thinking the same way when they go through their code, like what I learned and how you can get that performance back. And I want to bring up, I know people talk about data. ECS is all about data. Well, what does data have to do with performance? We all heard about the word cache. It's important for the cache. It's important to use the cache efficiently. It's important to do that. But those are things it's kind of well, why? Why was the cache there? Why is the cache not bigger? Why was it made this way? I have 3 or 4 gig of memory, well, 16 at this point. Why is the cache there to make my life harder? And that's kind of where I'm going to go with the assumption of why the cache exists. When it started, why did we create, well, not we, I wasn't there, but why does cache exist, and why was it based on what assumption was it based? And kind of going back to how, as game developer, we broke that assumption, which is why ECS is trying to fix that back. The way we're making game has broke that assumption, and has make it that the cache is less efficient for us. And then once we have that thing, I would like to go to how ECS align with those conceptions to kind of be well, how does that make it better for you so that you kind of you go back to the correct assumption of how cache works and you use the hardware correctly. So before I start, I should ask the question, which is an honest question. It's like, should you care about performance? Now, if you're all engineers, I don't know how many engineers will be like, obviously, I want my milliseconds. Just stupid to ask this question. But like, if you're a producer, or like any person, like an indie developer, and you have to worry about your budget line or like kind of things, like you have to ask yourself, like, is gaining that performance worth it? Like, I can already make a lot of game. I can already do a great game on the PC. Do I really need to care that much about getting the perfect performance? Do I really need millions of objects on the screen? Like, is performance just about getting tons and tons of objects on the screen or not? So my answer will surprise you, but it's yes. Like, I know it's surprising. But I want to go back to the concept of what making game is, right? Making game is about bringing your imagination to a hardware. There's a constraint on the hardware. So like we talk about making game being your game, like your imagination, your world, your thing to life, but you bring it through a constraint of the hardware. The first Zelda game, when I played it on the NES, was great, but it was constrained by the hardware. Like, I mean, they brought this world on a constrained hardware. It's completely different than the Switch. The Switch is like higher, like the hardware is a lot more efficient, and you kind of bring your world, your hardware constraints are different. It allows you to bring your imagination more. So I want you to think as performance not as about millisecond, but about the constraint we put on ourselves. So when we think about hardware, when we did the NES, the first NES game, the first GBA game, we were using the hardware to the max. We had no choice. We were like assembly language. You had no choice, or else you would not get anything on screen that would move correctly and stuff. So you had to use the best kind of hardware. And the more hardware evolved, the more we start looking about that constraint, about being, well, it can do enough if I don't do it correctly. That's fine. I'll just go about this stuff. But what we created is we created artificial constraint on what the hardware can do. And the perfect example is console games. Like, I'm not because I'm Intel, I'm going to say bad thing about console. Console are great, but like, if you get a new console, and I worked on it, like the first year games that are on a console are totally different than the game 6 years in the lifetime of the console. And the hardware didn't change, like nothing changed and nothing stuff. So like in theory, you could have done those games you did 6 years later at the first start. But you started learning how the hardware worked. You started getting that. So it didn't make it faster. It opened up the constraint so you can really bring your imagination back to it. So let's go to what is performance. So any work you do on the computer or on any piece of machine, you get data in, you do a transform on it, you do some work on it, you get data out. It's always the same case. Like if you don't get data out, then your work is just, I don't know what it's doing, but it's like global warming in some way. Like it doesn't add anything to the value. Like, so you're getting that out. But the way we think about it is like by habit. We think performance is the transform work. So like what we're trying to make faster is the block in the middle, the work part. So I want to kind of go into, and sorry, there's going to be some code. I should have one in advance, but simple codes. So like, let's say in my career, I would have seen hotspot code for some reason, some tool. I had instrumentation, the Unity profiler. And this is showing me this code is taking crazy milliseconds. It's slow. And I kind of go, and I just look at it, and then quickly I have a few assumptions about what might be wrong. Why is it slow? And those assumptions, I mean, we tell you should always use tools like to before to get, you should use vtunes, you should pix. By experience, that's not really what happened. Like, you're not going to always build a new executable to use an external tool to give you perfect data. You're going to look at the code, do some change, see the instrumentation goes faster, be happy, and then move on. And then you're only going to use external tools when, well, it's really, really slow and you can't figure out why. So back to this, you will look at this, and your first assumption will be, well, obviously, those really precise math operations that does really useful things are maybe too much. Like we may have too much code, too much work happening, too much multiplication, too much division. That random generator might be doing too much work. Again, that transform part, like we may be doing too much. It might be slow. We need to look at it. That loop count might be too high. We need to cut stuff in our game. It's just doing too much. That we have too much data that we need to process. We need to cut stuff from the game, lower the loop count. And because we're all Unity developer, that dot position, well, we should cache it because the get component cost is slow and kind of stuff. So let's try to assume, okay, well, what happens if I cut some of the work? Literally, I just remove all the work. Like I'm like, okay, well, if we don't, the only thing I leave is the random generator just because I have to have it for the example. And I'm just going to tell you, it's really, really fast. Like, it's not a problem. So I remove all the work. I kind of do the thing. So the result that I get is, it's before I had for example, in this case, I had I should have put 2.4. I don't know why I left 2 decimal, 2.4 milliseconds. And then I cut all my work. I mean, like, completely cut the work, and now I have 1.83. I saved about 25%. The only thing left is the loop count. So someone has to tell the artist designer, hey, we just don't have the budget anymore like you. I changed all the code. We can only have particles that are billboard facing the camera, not rotated in axis align or any kind of stuff. You just need to have less particle. Or what will really happen if I'm a rendering engineer, I'll go tell the design engineer that they need to cut their budget because I'm not cutting my budget. So they're going to go cut their millisecond budget. I mean, we all know that, so what happened? But I mean, it is a big point in a way, right? It's like we focus on the amount of work, and that's kind of what I was going to bring back about, like, that's what the impact of our game. Because this is going from millisecond number to what really matters, what you're putting in your game, what the type of stuff you're doing. Like, you're cutting stuff. Cutting stuff is not good. In some way, it's like you had put those stuff because you wanted them there. Like, you didn't put them just because you were, like, spraying unnecessary thing. Like, you wanted more than 2 characters on the street. Like, you wanted to be able to interact with the NPC and not just bump into them and not be able to have any kind of, like, nice interaction. Your FX artists didn't, well, maybe they did, but they didn't put tons of particles for no reason. They thought it would look good. I was an FX engineer, sorry, so I'm kind of going on FX artist. But it's kind of that concept, like that has a cost. Not, we look at milliseconds, but really, if you needed those calculations, you're going to cut stuff from your game to get them back. Well, I want to go back now, and we'll come back to that example. About then, what was that thing about caring about data we were bringing? Data equal performance. And this is kind of the history of evolution of processor speed versus processor performance gain versus CPU memory performance gain. 1980s, you could kind of say, like, okay, we started in 1980s. They had, those are relative performance gain, by the way. Like, you cannot compare performance of memory and stuff. It's just relative. Over time, memory gain, memory speed access has gone linearly. It's gone faster. It's a lot faster. Like, I mean, like, I don't know what are we at, DRAM 4, DRAM whatever. Like, it just goes a lot faster. You'll need faster memory. But processor speed has gone exponentially faster. So what it does mean is, like, what you could do in 1980, you could do a lot more calculation, like exponentially more calculation now than what you could do before. And what we call that is the processor memory performance gap. Because like we told before, it's data in, data out. Data in, data out mean I need to access memory, like data lives in memory. But the work part, the middle block, has got extremely faster. So if we go back to thinking about performance, our assumption that, like, our way of thinking was wrong. What performance is, because it's data in, data out, it includes those arrows. Like, it's not just about the work I'm doing. The time that it takes me to get the data and the time it takes me to write it is what I need to evaluate my performance, because we're saying if you don't write anything, then you did no work, really. Like, you're wasting time. So, like, when I'm measuring things, I'm measuring the time it takes me to get the data, the time I play with it, the time I send it back, and it gets written. So let's go back to our sample. We kind of go back here, but now we're going to focus on a different aspect, which is kind of just the data part, the data access part. And we're just going to focus on the read part, not the write part and the sum value, just the read at this point. And we're like just looking, okay, well, now that I know about data is important, data speed is important, what happens if I focus on it? So I'm going to change my random generator. I'm going to add more work to this, what we considered work before. I'm going to make my random generator more complex. Before, it was going from 0 to all it was randomly accessing index in the array. Now it's going to be more constrained. It's going to access I to I plus 2. It's still going to be random. It's still going to do the same amount of work. In fact, it's going to do more because now you have a min function and kind of stuff. You're doing more work, but you change where you're accessing your array. And so what you had before was 239, 2.4 milliseconds. You did your work reduction where you removed everything. You were at 1.8 milliseconds. And then you did the stuff with like, that example is kind of that concept of I made my data closer to each other. And then I got 1.23 milliseconds without changing any transform, any of the things that are part of the game in some way. Like my effect artist can still have the same amount of particles and kind of stuff. In fact, what they could have is I could do more multiplication, more addition, more transform access. They can now finally have those billboards that are access aligned. My designer can do more AI work. My environment artist can do more things in the environment that moves and are not just static kind of stuff. So by looking at how we access the data, we kind of like didn't change anything. We just realign our data in some way. That example is just showing a realignment of the data. And suddenly we're like a lot faster. And we find out that, oh, well, we weren't constrained. When we go back to that constraint fact, our hardware constraint that we thought, oh, the hardware is slow. Well, it wasn't really slow. It was just the way we used it was slow. Now, if we did it correctly, it's like, oh, well, we can do more. And that's back to that example of the console. First year, you get one type of game. 6 years later, you understand better the hardware. You get a lot better game in some way. And I kind of I want to bring back, I understand when people see that, they're like, well, I never do that, right? Those are obvious examples, and they're obvious examples because I have to put something in one slide. So I'm not going to put you 60 line of code or more. I don't know why I said 60 as it's big, but anyway. But we do that all the time, right? And this is just an example from Unity in some way, but the way game objects work. But our components in our game object are all around memories. If you do object-oriented programming and you don't do it correctly sometimes, which most people don't because we've never been taught to think about data, so over time the way you use object-oriented programming is not the correct way for the hardware, then you end up with your data, your fields, and everything are in random memory access. So if I was going through tons of game objects, and I'm like, give me the renderer for each one so I do my update, well, then I'm doing random access in memory all the time. So I'm doing that thing that I say I never do. But also, what this brings you is that problem. I had put hotspot in quotation mark. So for those that don't know, hotspot is generally that concept where we look at your entire game, you run a profiler, and your hotspot is that bar. If you look at your instrumentation in Unity Profiler, you see a thing that takes 2 milliseconds. You're like, I need to fix this. This is my hotspot in my code. This is why my code is slow. But really what you don't see, or maybe you think about, but everything else is slow. It's just that you don't have time to go through everything to get 0.005 milliseconds back. Something that even if you gain 50% gain on that other thing, the change is of the absolute value, the 0.005, is not worth it. But they add up. Everything else adds up. Those hotspots are just the obvious location where I have time to fix those, but I know everything else is slow. It's not physically possible to go back and spend my time just fixing everything else. The other thing is you might be okay, well, I don't have random access. I have everything perfectly aligned in memory and thing. Well, you have two exact same code, just the structure is different. And so that thing is as slow as like the one with the less, just one field, is around, I think, 55, I wrote it here, 56% faster. So kind of like I started talking about random access and like why it's safe. And this is kind of bringing you that example. The problem is not random access. The problem is locality of the data. So the code is the same. They're all accessing the position field. And I could have my structures perfectly aligned in memory. It's just that the position field on the first one, when I access it in memory, it's one after the other. The second one is like, well, I have position, then I have lots of other things that I don't care about. Then I have position, I have anything. And that's exactly the same as random access, right? It gives me the same bad access. So let's go back here in 1 second. So in our example, the processor part was the math operations, and the memory part was the data access. And then over time, the math part got faster. So if I ran the same code on an old computer and a new computer, the amount of data I can access has just gotten a little faster. Like I can access more data, I can have more particle. But the amount of math operation I can do has gone exponentially more, right? I could have done maybe one multiplication. Now I can do like, I don't know how many, but like a crazy lot. So I understand I show you why it's faster, but so why are we slower for random access? Again, I use that word random in the stuff. Like, I mean, you all have the idea. RAM is random access memory. It's in the name. And it's like, it's made to be randomly accessed. Like, what's going on? Like, why is it lying to me? Well, it's not lying to you. It's the same speed to access everywhere. It's just that accessing everywhere is crazy slow, right? It's the time that it takes it to bring it to the CPU. So I like to use the analogy of cooking. I'm at my house, I'm doing a recipe, I'm starting to cook, and then there's an ingredient I need. I get in my car, I go to the grocery store, I get that tomato, I come back, I start chopping it, start adding it. The next step is to get a cucumber, I go to my car, I go to the grocery store, I get it, I start chopping it and kind of stuff. So the tomato and the cucumber might be close to each other in the grocery store, but the time to go get each one is still the same. Like, if I needed bread versus another cucumber, I would have gone to another part of the grocery store. It would have been the same time to go to the other part of the grocery store. But driving there was the slow part. Like, it wasn't just, once I enter the grocery store, it doesn't matter. Like, I mean, I get everything fast. And I know this is the perfect analogy, but it's the same concept, like, right? You stop working on your cooking. And that's what the CPU does. That's kind of why I want to bring you back. It's like, when the CPU access memory, that slow part is important to understand. Like, obviously, it's absolute speed, it looks crazy fast for us. Like, if you look absolute speed, it will be like crazy fast. You can do work just accessing memory and doing it. But relative speed for the CPU, you have that cost of opportunity. While it's going to RAM to get information, it could have done other things. It's just not doing anything. And I want to bring back one more point here. When you do Windows and you use your CPU usage, the time it takes, like we're telling you your CPU doesn't do anything, the time it takes to go to memory to read is considered usage. So when you see your instrumentation saying 2 milliseconds of time, you don't really know if it's like really doing 2 milliseconds of work or 1.8 milliseconds of waiting for data to come and 0.2 milliseconds of work, right? So I told you before you need to understand the assumptions, like what were the assumptions we made to create the cache. And so I don't remember what year it was, I should have looked, but a long, long time ago, someone analyzed how code was written. Like, how do people write code? Maybe like before C#, before any JavaScript, before any code, like we just kind of come with that concept of how do people write code? What do they do? Like, what kind of data access is happening? And they came up with the principle of locality, which is either we do temporal locality or spatial locality. And so temporal is the location of memory is likely to be reused. So if I access something in memory, it's likely I will, in a short amount of time, need it again. So if we go back to our sample, I won't go back all the way, but I had that sum value. I was adding thing to the sum variable. That's the temporal locality. So when I got the sum variable from memory, I had to go all the way to memory to read what its current value was. Well, when I'm doing that loop, I'm reaccessing that sum variable nonstop to add additional value to it. So it's like I'm accessing the same point in memory a lot. Spatial is like, if I use a location in memory, it's likely that I'm going to use something really close to it in the short term. So it's kind of like that concept. If I have an array and I do a for loop on it, if I read a position I, it's nearly like most of programs will go I plus 1 on the next step. They will access the next position in the array. So that was what was happening before. And so those are the principles that brought, okay, well, if that's how people use, that's how people write memory, like they always use the same variable, they're always kind of, when they do work, they always access work really close together. Then I have an idea. I'm going to invent something called a cache. That cache is going to be really, really, really small. The reason it's really small is it's a different type of memory than RAM. It's really, 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 really fast to access. In fact, there's like, you could say that the register in your CPU are like the one that are the cache 0 in some way, then you have L1, L2 and stuff. But just let's focus on one cache right now. It's that idea that, okay, well, what I'm going to do is if I'm accessing a position in memory, you all heard about people talking about cache lines. Well, cache line are just that concept of memory. I know like a block of memory. I know I'm accessing a position. My principle of locality said, okay, there's a good chance you might need it again, and there's a good chance you might need the data next to it. So I'm going to get a block of that memory. I'm already going to the grocery store in some way to get tomato. I'm going to get all the veggies that I need because they're all close to each other, and I'm going to come. Same way for the memory. Like I'm going to memory, I'm going that long trip. My principle of locality said, well, I'm going to come back here for those things around here. So I'm just going to take 64 bytes of them around that, and I'm going to bring them to the cache. That's what the cache line is. It's 64 bytes next to each other. And I'm putting it in the cache. So the next time the CPU says, oh, I want the data that's really close, the I plus 1, well, the cache will be, hey, I have it, just take it. 4 cycle, really fast, like I just give it to you. And I was getting tired of making blocks and things, so I do it by hand and took a picture. But it's really hard. I tried to do blocks in PowerPoint of that thing, and that was not working. So let's go back to our structure, right? A memory, one of those small squares is a vector data. 64 bytes of the cache line, that's the block. And my array is just blocks of 64 bytes going up, like vector, 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 that block. So when I go, like I said, I get that block in. And that's an important thing to know. You always need to go to memory to get it. You cannot ever not have cache misses. You cannot ever not have to go to the grocery store to get your ingredients. You're always going to have to go to memory. Like it's not a magical thing. You're not just going to not have to go to memory. That's where your data is. The thing that you're trying to do is like, okay, well, I want to avoid the amount of time I'm going to memory. So I'm getting that block. I'm like, okay, I'm getting everything. I put it in cache. And that cache is really fast to go to the CPU. The next time I read something, it has to compare with the cache. It's like, oh, are you in the cache or not? Are you in is that square in the block that I have on the cache? If not, it's going to go. So I want to go back. I know I said it before. It's not the random access that is slow. It's the position in those blocks of memory. Are you in a block of memory? The data that I'm accessing next, is it in that block of memory that I already put in the cache or not? So if you remember the second example, when I had a struct that was just one vector, and I had another struct that was multiple field, why was that slower? But because the second struct was using more space in the block. I think the example I had the entire block of space, like 64-bit. So like the next time I use position, the next time I want to access position, the location is memory, is in another block. So that's a cache miss. That's another trip to the store that I have to go get that version. So exact same code, different way of accessing data. And so, sorry, that's kind of what I just said, but wasting blocks. That's what we mean when we say wasting block size, right? You have structures. Well, we say wasting cache line, but I prefer to call it block size, but it's my word. You have structures that are bigger. And I kind of want you to bring back that point in some way about the fact that when you're making game, we're not alone in making game anymore. Even NGs, you have 3 or 4 people sometimes, like you have friends helping you. So you may have written that struct correctly. Someone else might have added 1 field more in there, 1 debug field. Someone else would not really know about your thing, right? It's like kind of people will have added data without you knowing, and then suddenly your code is slow, but you will not really notice it because everything is slow everywhere, just a little bit. You just notice that your game is slow at some point, and then you just fix those hotspots. You don't go back to fix that 1 struct that now has 2 fields and not just 1. Okay, so back to Unity now. Like we all heard about ECS, so how does this align with ECS? Well, ECS is trying to fix what I was telling you. We had the assumption initially, cache was created with this assumption of principle of locality. And I'm telling you that we broke it. Like when we make game over time or language or like kind of stuff, we get the language are easier to write. They save us time to write the code. They're like easier to write code. But in some time, we break that principle of locality. We break the reason why cache is here to save us time to go to the store. So we're going to that grocery store nonstop. So what ECS is trying to do is to help you. If I use ECS, then I don't have to worry of making my data correctly. It's going to take care of aligning my data in memory for me so that when I access that data, I know for sure it's correctly aligned. Now, it's something that's important to know. There's never any, I'm sorry if no one knows it, but magic is not here. So there's no magic. Like you can look at the C# code, and Unity is very nice. Like I mean, all package, you can look at their C# codes. They're in the cache somewhere on your local computer. You can look at the C# code and figure out what it does, right? But let's go a little more in detail on what it does in the same way, like at the low level. And this is a little simplified view. I took that from Fabrice's talk from Unity. I borrowed it. But it kind of helps. It's the same concept. Like, I mean, the same way as now if you think about cache is crazy complex. Like, I mean, there's like, you go to like, I don't know how many years in CPU architecture to like do correct cache. But the concept, the initial concept is still the same. If you understand it, you can kind of understand what cache is doing in some way. And it's the same way with ECS. Like if you understand the base thing, you kind of understand why you have some API limitation, why you have some constraint being added, well, when people on the forum are asking, well, I would like to do this random thing or access this, it's like, well, you could, we'll always let you do that, but that's not the default, because the default is based on this assumption. So at the low level in ECS, the data is stored in chunks of memory. They call them 16K chunks. What you have is also an archetype. So I don't know how many of you use ECS up to now, but generally you have something called I-component data, which is just a struct, which says what data it contains. So if it's in this case, I have an I-component data of position, which will have 1 field, 1 vector float, like a float tree of vector. And then I have a rotation, same thing, it might be a quaternion. And then I have a renderer, which might have 3 other fields in that struct. And then I have an entity, is a thing that contains a certain amount of I-component data. But any entity, archetype is just a concept. Any entity that contains a position data, a rotation data, a renderer array data, is of this type of archetype. So you can have tons of different entities, but they all have a type, an archetype. They all have this 3-component data. If I remove rotation array from one entity, if I remove rotation, the I component data, if I removed it from the entity, then it goes to another archetype. It goes to an archetype that has two types of I component data, position array and renderer array. So what's a chunk? And I mean, the best way if you're reading code and knowing exactly what they're doing, this is like, look at this, go find this function and kind of get a great idea of how it does it. And then when you create an archetype, in the create archetype internal, you will see how it positions where the location of those things. But a chunk has sub-arrays. And I'm not showing everything in a chunk. Obviously, there's a header part at the start of the chunk, and there's a little bit at the bottom for all the I share component data, and that's seeing if the chunk has been touched. But those are small amount of data. Like the main part is here. There's also an entity array that I'm not showing, but it doesn't go with the concept is this guy, like, right? We have 16K chunk. I have my archetype says I'm going to have 3 I component data in it. So in this tree, what happened really is that 16K chunk gets separated in 3 sub-arrays. So it means that on my 16K chunk, I'm going to have my position array, my sub-position array. I'm going to have a sub-rotation array and a sub-renderer array. It looks in 2D right now, but if you're in memory, it would be position, followed by rotation, followed by renderer. And so what's an entity? Well, an entity is the same index. So like an entity that has those 3 positions will be at index 1, which is the blue case, of position. The rotation component that's part of that entity will be at exactly index 1 in that subarray. And it will be exactly at index 1 of the renderer array, right? That's why if you looked at previous, I think in Austin mic hackathon, I didn't see it stuck this time, but entities in ECS are really just that concept of index. There's an entity manager, there's other kind of way of accessing, but really in the end, entities are not containers. They don't contain things like we put component, but really they're just a way where, oh, I'm at position 1 in this subarrays of data. You can go there and stuff. And then when I go through my subarrays, there's no concept of entities. I'm just updating position of archetypes. There's a concept of archetypes, so I'm going to do a system that is going to update all the position for archetype that have position, rotation, and renderer array. And then I'm going to go through all the chunk and update those position. But there's no concept of per se entity. Now you can access them, but that's where you break a little. Like the more you do those things outside the sub-chunks, subarrays of those chunks, the more you start getting those problems. So what does this give you in some way? Like how does this relate completely to what I just spent some time talking before? Well, those subarrays, that's what Unity is going to give you. They're going to be perfectly linearly aligned. So if index 1, I decide to delete this entity, and I remove that second, like that, those blocks, I'm like, those components are not valid. Unity, the ECS system, will take care of taking something at the end, bring it back to replace it, and guaranteeing you that you would not have any gap in your subarrays, right? And the length of your subarrays, it kind of go back. So you have that concept. Okay, well, it gives me subarrays, I have linearly, but I only have 16K. So if my renderer array is one of those structs, my I component data is one of those structs that use tons and tons of field, well, I'm kind of wasting the space of my chunk. I'm using like a lot. I can maybe only have 3, 4 entities fitting in that 16K because of that amount. And if I don't, and that's fine if I use all the data in that I component data, but if I don't use all of it, then I've wasted that thing, and that goes back to wasted cache line. So data, ECS and cache miss. So data is linear inside the chunk subarray. It's going to guarantee you. So if you do the way they want you to do it, the default way, which is not, I mean, it's not the way they want you to do it, it's the way they made it. It's the assumption. That's how they wrote the code. So you access it. If you access it this way, what Unity guarantee you is like the amount of time you have to go to the grocery store is going to be exactly the amount of time that you really need because of the block size. You're not going to hit more block size access that you need. If your component data is at the right size also, obviously. You can break that if you put high component data that are filled of things you don't need. But as long as you do like the high component data has the exact data you need, Unity will take care of it. And no, I'm not saying you could not have done that before. Like they didn't create, like, I mean, all the code is in C#. You could have written that before. But Unity is kind of giving you, like you heard at the keynote, it's like you think of them as your engineering team. It's just that concept of they took the time to do the way you would have done it if you had time, of how do I put, okay, all my entities, I need my position everywhere aligned. I'm just going to start creating a system and stuff. Well, that's what the ECS is. They took the time to do that for you in some way, so you can focus on other things. But what you gain is that thing, if like I create an entity, well, every position of every entity, of every character will be aligned perfectly, as long as there's the same archetype. And the best way to access it, the lowest level way of accessing is you create a component group. And a component group is just a way of filtering archetype, right? It's like, I told you we have different type of archetype. A component group says, oh, well, I want archetype that have position. I don't care if they have other high component data. I just want archetypes that have the position high component data. I'm going to do something, I don't know what. Then I have, that, like I said, that filter. And then I can ask, give me all the chunks. And that's kind of the concept, right? You can ask it to give you those chunks we just talked about. But it's going to give you all the chunks. So like for every archetype, it's going to go through every archetype. It's going to be, are you part of that filter? It's like, yes, okay, you're there. I'm going to add you to the array of chunk. I need your chunk. And then I'm going to go to the next one. And I give you all the chunks that contain position high component data that you said you care about. And then you just go through the subarray the same way. You just ask it, okay, now every chunk, give me your position subarray, and I'm just going to go through it and stuff. And that might sound complicated, and they have iJob process chunk. They have things that are like, if you're doing the standard way, they have things to make it faster. Wrappers are on the code. But they're all kind of doing that kind of concept, right? They're going through it and giving it for you. And again, I want to repeat, you can break that if you make your high component data too big. Like you do have a responsibility to still make sure you're not wasting block size. So now I talk about ECS, and I know every people is excited about job systems, right? The ability is like, well, why did this Intel guy talk about data access and not about the fact that they have 18 core CPUs now, and I could use all of those, and I could make the greatest game in some way. But I talk about this because data access is crazy important, right? It's like you could like spread on all the cores. You could have done that before also. Like, I mean, dual core came out like, I don't even know at this point, like a kind of stuff, but they came out a long time ago. Like, multi-threading is not something new. But we all heard that joke about like, if you have a bug, you can write multi-threaded code and you got even more bugs. Like you're just creating yourself a problem. Like why would you do that? Well, the funny thing is if you go to any language, any programming language, and you go to Google and you say, give me a sample of how to write a thread, it's really easy. You can write a code that will run on threads really, really easy. Like it's not writing multi-threaded code is not hard. What is hard in multi-threaded code is the data access. The fact that you have threads fighting for the same data access, trying to modify at the same time the data, trying to do stuff. So data is the part that is hard about multi-threaded. And I did it before. I mean, the same, like if you took a sample and you're just the only programmer working on it, it's fine. You can make sure your struct is every correct. You can make sure your class has the correct data. You're perfectly fine. You add a second programmer, you add a third one, you add a fourth one. You cannot control everybody. People can write threads accessing data in your class differently, so you get that problem going. So Unity created that job system that has a safety system for you. But ECS is the thing that feed the data that its job system needs. That job system, that safety system that allow you to say, hey, I'm writing to that native array, don't read from it, and it's going to tell you a warning, your job and stuff. It works by native array, and we just saw that chunks in ECS gives you those native arrays. So ECS is the way to make your game create native arrays so you can feed it to the job system that will give you that ability to write code that works for all your data and not just specific amount of data. And the last thing I wanted to bring back is the performance by default part of what Unity is saying. I have a way of seeing it. It's generally the way we work right now is we write code and we think of performance as the work we need to do at the end to get more performance. Performance by default is a different concept. If you use ECS and the job system correctly, you get that full performance. You're at the limit of the hardware, as close to the limit as you can be. Like you have maybe some thing, but you're really close. And the additional, if you leave what the default is, you could get faster, but you choose the risk of being slower. That is what the default is. You do not have to worry about how I would need additional time at the end of my project to change those hotspots everywhere to make them fast. You start thinking differently. You start thinking, oh, well, I'm just going to focus on my game. And I'm just going to know that if I follow the default way that Unity wrote ECS and job system, I will get good performance. And if I need to do something specific, then now I know this is risky and I need to be extra careful on it. And yeah, that was me.